So now that we've talked about what black holes are, we are going to get into a little bit of how to describe them. And the first part is the Schwarzschild radius. So just how big is that black hole? Well, that's something that's actually fairly straightforward. The radius of a black hole is 2gm over c squared, where g is Newton's gravitational constant, c is the speed of light, and m is the mass of the black hole. So, using some familiar data, if we were to turn the Earth into a black hole, well, we would have the 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Earth's mass is usually around the 5.97 times 10 to the 24. So that's our best estimate of it. And the speed of light is that 3.00 times 10 to the 8 meters per second, and we'll square it. And this will produce the radius of the Earth if it were a black hole. It's easy enough to calculate. Go ahead and do it yourselves. But you will get that it's 0.00885 meters, or roughly 8.85 millimeters. That is right. If we were to take the Earth and squeeze it down to turn it into a black hole, it would be less than a centimeter in radius. If we were to do the same with the Sun, where the mass of the Sun is more like 1.99 times 10 to the 30 kilograms, well, we can take a look at the proportions there and see that, yeah, it's about 300,000 times as massive. So we'd expect it to be about 300,000 times bigger. Which it is, but even then, we are still only looking at, less than 3 kilometers. So if our sun became a black hole, well, it's the kind of thing, if we're looking at a 3-kilometer radius, well, we're looking at an 18 to 19 kilometer circumference. The radius is more like 2.95 kilometers. So that makes the circumference more like 18.533 kilometers, or about 18 and a half. There are people who will jog that on a regular basis. So they would be very small. And this is part of what makes them hard to spot. But it also has another side effect. If you look at the density of an object, let's say our black hole is a sphere. Well, the density is mass over volume. So that's mass over 4/3 pi r cubed, where r cubed is 8, that's our 2 cubed, g cubed, m cubed over c to the 6th. So our density of the black hole, if we bring our 3 up and start substituting in, we'd have 3m c to the 6 over 8 times 4 makes 32 pi g cubed m cubed. Or canceling that common factor of m, one of these cancels and one of those cancels, we end up with the m squared we find that the density of a black hole is a collection of constants times 1 over the mass squared. So in other words, the mass or the density of a black hole decreases as the black hole gets more and more massive. So as you add more mass to the black hole, the density of matter within that black hole goes to 0. So there were a number of questions people had. Is it possible, given this, that the entire observable universe is inside a black hole? Well, you crunch the numbers on the mass of the entire observable universe and our estimate of what that is, compare that to the observed density of the universe, and based on this idea alone, it does seem possible that we are completely contained within a black hole. It's not likely, and when we get to part 6, we will find out some of the other side effects of living in a black hole that will make us seem a little less likely that that is the case. But that's part 6. First, we have to deal with part 3. Black holes have no hair.